Perfect. Yeah, so thanks for the introduction and the invitation to talk. I think this is kind of a perfect complement. So credit to you, Manish, for kind of organizing collaborative or closely defined talks. So yeah, today I'm just going to kind of review my PhD work and then talk about what I've been doing at AFRL for the last few months or so. And I know my title is kind of word vomit, or kind of looks like SpaghettiOs. So I just kind of wanted to use a disambiguation to kind of set the stage for what I'm going to talk about today. So when I talk about nonlinear in structural mechanics, I'm focused on nonlinear responses due to contact, material nonlinearities, or large deformations, and precisely pretty much, or generally, nonlinear responses enact a change in the stiffness matrix as a function of your state variables. And those simulations require iterative solution methods, and they're computationally expensive. So that's kind of the motivation in terms of computational expense. We're using substructures, which is a way to pre-compute and save essential structural information from the linear physics down to a reduced set of degrees of freedom or nodes for efficient computation on the linear side. Then computational plasticity, we're using the mathematics that was developed back in the 30s and 40s, but we're applying it to substructures in the nonlinear sense. And I'll get into all of that. And then finally, when I talk about efficient design, I'm specifically, at least for this talk, interested in, or I'm going to be talking about, kind of these heterogeneous bimaterial or multi-material unit cells that you could feasibly enact a plug-and-play design strategy to better design an overall macro structure. So we're kind of doing a meso to macro scale design process. And so, Emma, if you have to leave, I hope you stay, because I'm going to stay for the next minute, because I'm going to give away all my secret up front. So pretty much three things to take away from my talk. The first is we need reduced order models for nonlinear multiscale structural responses. And I'm specifically going to talk about adaptive structures because they're inherently nonlinear, and a lot of them demand multiscale analysis. A second point that I want to make, and then I'll get into this later, is that we can kind of couple substructure analysis and the mathematics of plasticity to provide a reduced order modeling framework. So this is kind of a complement to a lot of the machine learning methods, where instead of taking a physics inspired physics informed based, we're taking a physics inspired based, where we're trying to embed the physics right into the model formulation itself. And lastly, I'll talk about a little bit of preliminary work where we can achieve 3 orders of magnitude in reduction to computational cost. And I need to caveat all this by, this isn't a silver bullet, but I hope that it provides kind of, at the least, academic curiosity in terms of using different parts of mechanics in reduced order modeling and machine learning literature. Okay, so as a motivation, pretty much, as I said before, adaptive structures demand multiscale analysis. So in this example, I have a sweep morphing wing that goes between a loiter and a high lift phase, depending on the mission stage. And in this problem, if we're not considering microscale damage, we have 3 distinct Planck scales. We have the mesoscale of each unit cells. And at this unit cell scale, we need to consider any nonlinearity that happens within that cell. So large deformations, plasticity, hyperelasticity. Then we have to consider the macro scale. So the entire sweep morphing wing component, where you have an array of these unit cells. And then you need to consider unit cell interactions and maybe heterogeneous arrangements of unit cells. And then finally, at the structural scale or the vehicle scale, we need to consider the interaction between maybe the adaptive structure of this sweep morphing wing drone, and then other components from other subsystems, like your actuation mechanisms, your flight control surfaces. And all of that needs to be incorporated in, because especially with an adaptive or highly deformable structure, if you don't consider everything as a full system, you could run into problems later on where two subsystems are contacting each other because they were designed independently of one another. So that's really why we need this entire multiscale analysis. But the problem with multiscale analysis is that it's infeasible during multidisciplinary design. So if we consider this n-squared diagram, where inputs are denoted by the dots coming into the tops of each of these boxes and outputs are denoted by the line coming out this way, if we want to consider one design through the entire multidisciplinary kind of process or multidisciplinary performance metrics that you need for a sweep morphing wing or any other adaptive structure, this entire loop is computationally infeasible for the fidelity that we need. So if you design your geometry, your materials, and then you run structural analysis, this blue box alone, for that example, would take around 24 CPU hours to run at high fidelity. And that's just because of the inherent nonlinearities baked into the problem. Then when you consider FSI or controls or some sort of actual mission, putting all of that inside of one optimization loop means that you're running one individual in an optimization in a few days, and that's just computationally intractable. So what we're focusing on here is if we can make this blue box, instead of 24 CPU hours, if we can make that orders of magnitude faster, then we can enable this entire design loop. Obviously, FSI is also inherently very expensive, but there are other people doing very similar things in that field as well. So on this slide, I kind of have a survey of the amount of physics that you can embed or incorporate into a different reduced order modeling approach. So on the left here, we have what I would call physics agnostic approaches, and these are pretty much surrogate models or curve fits. So you don't have any physics or any information about mechanics baked into the problem itself, but you can you can run these very fast. And then in the middle, we kind of have physics informed or physics inspired methods. So these are the physics informed neural nets. There's another work from AFRL and actually the University of Wisconsin that's called non-intrusive reduced order modeling. And then what I'll be talking today is nonlinear substructures. And then on the right, we have physics-based methods that are pretty much just applied linear algebra, so multigrid method or GMAC. And so each kind of silo or each characterization has different pros and cons. So physics agnostic approaches are really fast online. So they take, right, it's just a functional evaluation. You don't need to do any iterative solution, but you lose fidelity in terms of satisfying conservation laws. It requires training or calibration. And depending on your data set, it's very hard to generalize, and it's very hard to produce a robust solution. In the middle, the physics-informed or physics-inspired approaches can include conservation laws via constraints or the formulation, and there's a medium online computational cost, but we still require this training. And then on the far right, these methods, since they're essentially just applied linear algebra, they don't require any training or calibration, and you can capture the full set of field variables that you want, but they have a really high comparative online computational cost because you're solving the entire problem at multiple scales. So today I'm going to focus on the middle section, but really in the future, I'm going to try to look at everything to kind of build off of what Professor Lejeune was saying about kind of establishing value propositions for each of these different methods depending on the application of interest. So that was the kind of introduction, and now I'm going to go into describing substructure analysis and computational plasticity in turn, and then I'll talk about how we can couple these to make a reduced order modeling framework. So substructure analysis is actually a pretty old technique. It was first developed pretty much on the onset of computers because structural stiffness matrices were too large for computers back in the 60s. The working memory of a computer was too large to store a stiffness matrix of an entire airplane. So substructure analysis came around as a way to pre-compute and store essential structural information from, say, each one of these different subcomponents of the aircraft, and then use that pre-computed information to run the entire analysis. So notionally, what we do is we retain only the essential degrees of freedom, but capture the response of the entire body. So in this case, we have this complex unit cell, and we define the corner nodes, so those 8 degrees of freedom, as the essential degrees of freedom. And then we can also impose constraints on these interfaces, like linear constraints, a NURB, or whatever you want there. So this gives us a way to efficiently store all of the information in the linear sense of the stiffness matrix, but just as it relates to these 8 degrees of freedom. And so this really matters because it provides a method to exactly compute the linear response of these complex structures with respect to a larger assembly. Obviously, I want to be clear, this is only working for linear, and this is built off the static condensation literature. So there's definitely better ways to do this if you want to just use this to capture nonlinear responses. But this gives us a framework that we can use computational plasticity for. And so computational plasticity, or at least our approach where we assume small strains, assumes 4 main components or 4 main ingredients to our algorithm. The first is we have an initial linear response that can either be isotropic or anisotropic. The second is we have a yield or a transformation stress. And that yield or transformation stress is defined by a criteria. So this criteria itself can also be isotropic like a von Mises, or anisotropic like a Hill, or a Hill generalized quadratic. So with those two, the assumptions 3 or 4 are that the yield surface and our nonlinear state variable, in this case, plastic strain, they both evolve in a certain way. So plastic strain can evolve in a non-associative or an associative way, and then the yield or transformation surfaces can evolve either isotropically, so it just the yield surface grows, or it can evolve kinematically, where the yield surface shifts through stress spaces. So these are the 4 main ingredients to or at least the computational plasticity models that we're using in this work. And the point I want to make here is that there's a ton of freedom and there's a ton of existing literature from the great mechanicians that have been working on this for the last 60 or 70 years. And we have a lot of flexibility to capture a wide range of material responses. And what we did for this work was we applied this same framework to capture structural behavior. So instead of talking about the relationship between stresses and strains, now we want to apply this to describe the relationship between forces and displacements. And a lot of structures resemble very similar phenomenological responses as the plasticity models. So in the case of, if you have an infilled SMA lattice, so this is 3D printed NiTi, superelastic NiTi with a PDMS infill, you'll have an initial linear response, a force at which nonlinearity initiates, where the SMAs are either undergoing transformation or there might be damage accumulating at the joints. This nonlinear response evolves in a certain way, and then upon unloading, it'll come back. It'll either come all the way back to 0 if there's no damage because the SMA deformation and the PDMS deformation is recoverable, or there will be some irrecoverable displacement due to the damage accumulated. And so this is one example, but the same sorts of ingredients can be applied to metal structures by using, say, an asymptotic hardening law instead of a nonlinear smooth hardening law. And then finally, metal foams, you could capture this same response by using a nonlinear softening law. So these are just 3 examples, but pretty much feasibly, you can cover anything in this gray shaded region by just taking a different component from the plasticity literature and plugging it in a way that represents the phenomenological force displacement response of a specific structure. So I skipped over the math, and I can go through the math. People can email me for the math if they really want. But this sort of method in terms of using computational plasticity with substructures has 3 potential benefits. I'm not going to speak to how worthwhile these benefits are, or how strongly each one of these points should be taken. But potentially what we could do is we can borrow from the robust literature on plasticity, so we can have a wide range of flexibility to capture a wide range of different structural responses. Second, because we're borrowing from plasticity models, each model parameter is analogous to a material property, and on the structural scale, these model parameters still have physical meanings. So instead of like a traditional machine learning approach where you have a lot of hyperparameters, you have a lot of weights on all of your neurons, all of those kind of get muddled together, and it's very hard to extract a physical meaning out of one specific weight for one specific neuron. When we use our model parameters that are analogous to material properties, we can have a physical meaning because each one of those represents something like yield force or etc. And lastly, because everything has a physical meaning, we hope that the resulting reduced order model is more interpretable. So because you can tell what happens when you change a certain property, you can understand what's happening in the model formulation itself. And then hopefully it's more generalizable because it requires less training data, and because we baked in conservation laws to the formulation itself. So we should be able to apply it to more problems. So as an example of this method, a very notional example, we take a homogeneous square that's meshed with one element, and the material is assumed to obey linear isotropic hardening. So very simple model, but we're really just trying to answer the question, can we even apply the mathematics that was developed for plasticity to a structural problem? Because now we're going from the six unknowns of stresses and strains to 8 unknowns. So it's pretty much a question of dimensionality. And the math is here. It's additive decomposition of strain, anisotropic yield criteria, and then associative flow rule and linear hardening. So we're pretty much porting over everything from your graduate level plasticity class, and we're trying to use it as a structural reduced order model. The framework in terms of actually implementing of this consists of 3 main stages. First, we have to generate training data. So we perform high fidelity FEA on the substructure for many different load cases. And I want to highlight that many, in our case, says anywhere between 10 and 20 different load cases. So training load cases for machine learning, as you saw in the last talk, those numbers go as high as 10,000. But now we see diminishing returns as soon as you get over 20 different high fidelity load cases. So that's providing rationale for that. This is more generalizable in terms of the training data set. But with that training data set, we then need to calibrate our model parameters similar to training your neuron weights. So in this case, essentially all we do is we optimize the material properties, or the analogous material properties, so substructure parameters that are highlighted in blue, and we find the combination of those that best approximates the training data. And then finally, we verify by testing the ability of the substructure to predict high fidelity FEA response, either by holdout validation or leave out validation, or comparing to an assembly of these different substructures. And so I'm going to skip over the calibration process. I'd be happy to answer questions about that later. But when we run through those 3 stages and we get to the third, in terms of holdout validation for this simple example, error is quantified by the distance between these red and blue lines. And depending on the size of your screen, you might not even see a difference between the two, which is what we would expect for such a simple example. But this gives us confidence that using computational plasticity as a reduced order modeling framework has at least some potential. So we do very well in terms of a left out training case. And then when we also apply it to an assembly level response, So this is the sweep morphing wing example from the first few slides. And if you construct the sweep morphing wing from 12 different unit cells, each one being the homogeneous square, and we look at one node of interest, the red and the blue again, where blue represents the high fidelity FEA and the red represents the substructure, they're pretty much right on top of each other with less than 0.5% of error. And pretty much all the other nodes show the same response. And obviously, again, I need to caveat this. You aren't going to be designing a morphing wing by just plugging in squares of homogeneous materials, but this at least gives us the belief that we can use this for more complex problems down the line. And so that's pretty much the bang box right there, is that this framework, drawing or taking inspiration from plasticity and applying it to a substructure framework, can accurately capture these nonlinear structural responses. So the third kind of point that I'd want to make is that with complex unit cells that are computationally expensive, we could feasibly achieve a 3 order of magnitude reduction in computational cost. So to motivate that, as I started in the beginning, the goal of this work is to enable efficient and accurate design of these hierarchical adaptive structures. So in this case, if we have a chiral unit cell, one instantiation of this in high fidelity FEA takes around 45 minutes to run. So even though it's not as expensive as the full structural, full wing or the full drone or aircraft model, it's still very expensive to run in terms of optimization, because if you want to change each one of these unit cells independently, the design space dimensionality soon exceeds your computational availability or your computational resources. So for this second example, we're using this chiral unit cell, and the light blue material represents a flexible polymer infill, and then the stiff or the gray material represents a superelastic SMA. And then we've assumed in this case that our unit cell boundary conditions will remain, or unit cell boundaries or interfaces will remain straight. And obviously you can see down here, that's not a great assumption, and we're working to improve that right now. So this example has around 10,000 degrees of freedom, and we're going to try to reduce it down to 8 using 40 unknown model parameters. And we're going to try to capture large deformation, SMA constitutive modeling during the forward loading, and then complex geometry in terms of you have the circular feature embedded with these beams, and then also infilled with flexible material. So after running through calibration, we can see that the best training case gets 1.5% error. So around an order of magnitude higher than the very, very simple example, but it still gives us, it's still pretty dang good when you go from 10,000 degrees of freedom down to 8. So you can see pretty much all the way through, we hit the onset of nonlinearity and match the stiffness after nonlinearity has occurred. And this is for the best training case. If we look at maybe a more representative training case of our calibration is at around 3.5% error. So now we start to see a little bit of problems where in some cases, so the first line on node 3, I'll use my pointer. We kind of miss this onset of nonlinearity and then miss the hardening slope afterwards. And then especially with node 4, we don't hit this softening response at all. And I really think that this is just due to the lack of a non-associative flow rule that we haven't included in the framework. So if we include a non-associative flow rule instead of an associative flow rule, we should be able to capture a lot of these non-dissipative responses a lot better. But overall, still 3.5% error. We still do quite well with respect to a lot of the degrees of freedom. So how does this work when we plug it into an assembly? So if we take our chiral assembly again, and we look at 2 nodes, so node 17 is the upper left over here, we don't do well at all. So this is humbling for me to sit here and talk about this when I'm not showing good results. But essentially, we kind of hit the onset of nonlinearity, but we don't capture this re-stiffening behavior at all. The prediction gets a lot better when we go to node 20, and we just kind of underpredict the entire nonlinear response. And I think that we hypothesize that this is, these discrepancies are due to three main reasons. So the first of which is we use a small displacement formulation right now, and especially some of these unit cells up here at the top, they go through finite rotations. So that's really why I think we're missing this re-stiffening behavior. It's because we don't actually rotate the stiffness matrix, and I'm working on that right now. The second one is the unit cell boundaries, or the interfaces between the unit cells, are constrained in the substructure to remain straight. And obviously, these interfaces kind of obey more of a quadratic or cubic or a sinusoid even. So right there, we're losing the strain energy compatibility over those interfaces, and that would definitely contribute to error. The last of which is we have a 40 parameter calibration space. So that involves optimization of 40 different design variables. And that's a very large optimization space. So if we can embed unit cell symmetries, because each one of these geometries has a certain amount of symmetry in it, we could reduce that calibration space down to a feasible number of design variables, and we would get better calibrations out of it. But what I want to highlight here is, even though I'm showing you objectively poor results, we can attain a 3 order of magnitude reduction in computational cost. So, and that's agnostic of the calibration accuracy. So I believe that if we fix these 3 things and we implement these 3 algorithmic improvements, we will still get this 3 order of magnitude reduction in computational cost, but with much higher accuracy. And that's really what I'm doing in my first few months at AFRL, is implementing these enhancements and kind of testing out that hypothesis. So in conclusion, I hope this talk has kind of piqued a few people's interest about using, say, a constitutive law, or borrowing from constitutive modeling or mechanics to use in machine learning, or a reduced order modeling frameworks. Because so just in the case of computational plasticity, we showed that it could work pretty well, but I'm sure that that analogy could extend farther than just computational plasticity. In terms of future work, I'm planning on doing those 3 kind of enhanced calibration methods. And then I wish Emma was here, but she was talking about comparing different methods across a wide range of data sets. I kind of want to do the same thing for a more meso to macro scale reduced order modeling approach. So establishing a value proposition for each one of the different methods that I talked about in the first few slides, to see if this method that we've developed in the last few years is actually worth anybody else's time. And then the last 2 is, I've talked about macro force displacement responses, but the elephant in the room is any sort of failure or damage. And that's what I'm also working on up at AFRL. I'm working with the composites performance team up here to try to integrate progressive damage in to get a homogenized response of damage with my substructure prediction as well. And I'm going to talk about one of these more in depth because I'm kind of interested in it and I kind of want to get it out there. So each one of these unit cells has a certain amount of geometric symmetry. And right now, we don't assume any of that for calibration. We just say we have 40 parameters. We kind of hit it with the brute force optimization, but we can use group theory to reduce that calibration space. So group representation theory, or point group theory, provides mathematics to describe symmetry. So these groups could be simple objects like shapes. They could be complex objects and complex operations like taking a circle to a trefoil to a figure 8, all of those are in the same group that's represented by some mathematical transformation. And then these groups can also be just abstract or not even really mathematical. And group theory is commonly used in chemistry to determine molecular symmetry and then simplify molecular vibration. So you can see that this atom or this molecule has a certain amount of symmetry baked into it. Group theory was originally used to help simplify the differential equations to really eke out or to solve the vibration equations. And if any chemists are online, I'm probably butchering that explanation, but that's how I understand it. But instead of using this for chemistry, what we can do is we can extend the same concepts from point group theory to structural stiffness matrices. So this was a paper out of Cambridge 20 years ago or so. And they looked at this triangular pin jointed structure. And this triangle structure has 6 inherent symmetries, right? You can rotate it 2 times. You can mirror it about 3 axes. And then you have an identity symmetry as well. And then this actually is the structural equivalent to an ammonia molecule. So it has C3V symmetry. And by applying group theory, what you can do is you can rearrange the stiffness matrix to go from your general stiffness matrix, which I've shown the absolute value of the stiffness matrix to give a comparison, where pretty much every single component of that matrix is filled in besides 8 or so. And you can tell that there might be symmetry showing up because, okay, this box here is the same as this box here, but you don't really know. And what group theory allows you to do is kind of transform this matrix into a symmetry adaptive space, where now instead of 14 unique non-zero components, you have 4 unique non-zero components. And this is really powerful for solution, because if you have a very large stiffness matrix and you apply these same things, you can solve each one of these blocks separately. So you block diagonalize the matrix, you can more efficiently solve. But really what I'm interested with this is applying this to overcome the cursed dimensionality with calibration. So in our calibration, we have to fit or find the components of a quantity that's analogous to a Hill's general quadratic, or an anisotropic influence tensor. So in 8 degrees of freedom, we need to find 36 unknowns. And that's kind of the examples that I've been talking about today. But as soon as you double the degrees of freedom, you are adding an order of magnitude of unknowns. So if we want to extend this method to 3 dimensions, we quickly can't, because we run into the cursed dimensionality in terms of how many unique parameters we have to find. But for a lot of unit cells that we're investigating, there are inherent planes of symmetry. So for this BCC infilled lattice truss, we have 4 planes of geometric symmetry, and we can reduce the number of unknowns by a factor of 3. And that makes it, 1, easier to optimize. So instead of optimizing over 36 or 40 unknowns, now we're optimizing over 15. And it results in a generalized solution because the solution is rotation agnostic. And actually, so I don't have any results to show on this, but we've seen around a 50% reduction in training and testing errors by leveraging these sorts of techniques. So I think it's one of those things that's unique to using more of a physics-inspired approach, because you couldn't use group theory or point group theory to extract your symmetries from a machine learning algorithm, other than just adding more and more training data, right? So I think this is one of the real powerful things about using a physics-inspired or a mechanics-inspired approach, is that you can use the same techniques that were developed and improve performance that way. So with that, I hope I didn't take too long. My email's down at the bottom, and then I'd like to acknowledge AFRL for funding. So I'll take any questions.